Hi, welcome to the Unit 7 Day 4 example video. In this video, we're going to look at how to solve these example problems using the one-line method. So the emphasis will not be on going through each and every step and showing you how to calculate molar mass or all those different things or how to balance the equations. Although those steps are necessary for solving the problem, it's really going to be on setting up these line problems. So you really only want to do this if you are confident in how to calculate molar mass and how to balance equations. If not, you may need some extra help videos. Okay, so what I've done is for all of these problems, I've already read through them and identified the given and find. So I won't go into too much about that. And then I also calculated the molar masses for everything that I needed the molar mass for using the periodic table. Okay, so in setting up these one-line problems, when you're solving, after you've identified your given and find, you're trying to go from the mass of the given to the mass of the find, your one-line problems will look like this. You have what you're given in grams over 1. Then the second fraction will be the conversion factor that converts from the mass of given to the moles of given. And so that will come from the molar mass of the given substance. Then the third fraction will be the conversion factor that you get from the molar coefficients in the balanced equation. So you go to the coefficients in the balanced equation, and therefore you can use that to cancel out the moles of your given to give you your moles of find. So at this stage you have your moles of find. The last step is to convert from your moles of find to your mass of find by using the molar mass of find. And so again, you get the molar mass from the periodic table. All right, and when you do this process, you will see that the grams of given cancel out, then the moles of given will cancel out, and the moles of the find will cancel out, leaving you with mass of find. All right, but it's all done in one line and it actually saves time when you do it. So let's go ahead and get started with this first problem. So in this problem, we're trying to convert from 14.6 grams of sodium metal to grams of sodium chloride. So this is our conversion. So we're going to start with the 14.6 grams of sodium. I put it over 1 just to make it into a fraction. Now my second fraction is going to come from the molar mass of sodium. I already looked that up. And that way I can convert from mass of sodium to moles of sodium. So I want to cancel out my grams. So I'm going to take the gram part of that conversion factor and put it opposite, so in the denominator in the second fraction. That way my grams will cancel out. Oops, well, that's fine. Grams will cancel out, and then I get 1 mole of Na on top. Okay. So now I have moles of Na. Now I want to convert from moles of Na to moles of, so if you look at the process here, we're here, moles of Na to moles of what I'm trying to find, NaCl. And for that, I'm going to use the coefficients in the balanced chemical equation. So looking at the chemical equation here, I want to get rid of moles of Na. So that's going to go on the bottom. And the number, I'm going to get that from the coefficient. Now there's a coefficient 2 here, so I can put a 2 here. And I'm trying to get to moles of NaCl, so moles of NaCl go on the top, and the 2, there's a 2 in front of that as well. Now if you wanted to, you could write this as 1 over 1, because 2 over 2 is the same as 1 over 1. When the numbers and the numerator and denominator are the same, then you can just make it 1 over 1. All right, so now we've got our last conversions, because we're at this point, we've got our moles of find. Now we need to go to the mass of find. So to do that, I'm going to again use the molar mass. And for this, I now have moles of NaCl. So right now I have moles of NaCl. And it may be helpful to actually just cross things out as you go so you can see where you're at. You've got moles of NaCl, so you want to get rid of that. That means the mole of NaCl in this conversion factor must go on the bottom. And then the mass must go on the top. This is for NaCl. Okay, so now in terms of what does that look like mathematically speaking, this, you're multiplying fractions, so you multiply straight across, so you got 14.6 times 58.44 in the numerator. Oh, times 2 as well, sorry. 14.6 times 1, which you can ignore, times 2 times 58.44. And then the denominator, you've got 22.99 times 2. Okay, and so you can go ahead and just plug that into your calculator. Now, of course, you don't have to do all these steps out, but I'm just wanting to show people if they're like, how did you get that number? So now, after I've multiplied those two things, I would divide these two numbers. And don't forget what your units are, it's grams of NaCl. So what this is saying, that if you have 14.6 grams of sodium and you have more than enough chlorine, so that's not going to run out, it's in excess, you can make 37.1 grams of sodium chloride. All right, let's take a look at the next example. So we're going to do the same thing. We are going from, in this case, we're going from mass of magnesium oxide to mass of water. So let's take our magnesium oxide. Put it over 1 to make it into a fraction. The second fraction is going to come from the molar mass that I used to convert from mass of magnesium oxide to moles of magnesium oxide. So we're at this point, we're trying to do this conversion. So to do that, I use the molar mass, which I got from the periodic table. I want to cancel out grams, so the 40.31 grams of magnesium oxide go on the bottom, and then the 1 mole of magnesium oxide goes on the top. And it's nice because you can see those units cancel out. Now we have the moles of magnesium oxide. We now need to convert from moles of magnesium oxide to moles of what we're trying to find, which is water. And so for that, we would use the coefficients in the balanced chemical equation. So there's a 1, and there's technically an invisible 1 here in front of magnesium oxide. I'm going to put 1 mole of magnesium oxide on the bottom. Remember, I did that because I need the moles of magnesium oxide to cancel out. And then the 1 mole of H2O on top. All right, the last fraction is going to be used to convert from moles of H2O to mass of H2O, and for that we would use the molar mass, which I got from the periodic table. So I put the 1 mole of H2O on the bottom from that conversion factor so that these can cancel out, and then the 18.02 grams of H2O on the top. So when doing my math, it's simple. It's 17.3 times 1 times 1, which is just 1 times 18.02, all over 40.31. Oops, so 17.3 times 18.02. I'm just going to do this all in one step this time, divided by 40.31. And we get, 7.73 moles. Sorry, not moles, grams of H2O. Okay. It's like 3 o'clock in the morning here, so I'm a little tired. Anyway, that's the mass of H2O that we have. Okay, let's do the last set of examples. So we're converting from grams of strontium to grams of strontium oxide. So let's start by now I'm going to convert to moles. Now I'm going to convert from moles of strontium oxide to moles of strontium to moles of strontium oxide. And then lastly, I'm going to convert from moles of strontium oxide to mass of strontium oxide using the molar mass I got from the periodic table. Time to do my math. And when you plug this into the calculator, you get 11.7 grams of strontium oxide. So that means that if you burn 9.87 grams of strontium oxide with excess oxygen, so the oxygen, you have more than enough of it, the most strontium oxide you can make is 11.7 grams. All right, let's look at this next problem. So this next problem, the process is the same, but before we move forward, you know, the first step is always to check to make sure the equation is balanced, and if it's not balanced, to balance it. Now, in most of these problems, you'll notice when I balanced them, I broke all of the elements down into the, the different types of, all the molecules down to the different types of atoms that make up the molecule. But in the case of this type of reaction, like 4 and 5, these are double displacement reactions. So in these examples, the best thing to do instead of breaking them down into all their individual atoms is to break them down to the anions and cations of an ionic compound. So the cations are usually they're usually metals, with the exception of NH4 plus ammonium. And those are written first. So the first part will go first, and then the last part, which is your cation, will go next, right? And so you break each of them down into their anions and cations. Notice that this SO4 is a polyatomic anion that stays together. We didn't break it down to S and O. And that's because in a double displacement, they're just exchanging cations and anions. So since the SO4 stays together, those atoms don't break apart. We can treat that as one group. So that's the only thing I really wanted you to note here, is that that's how I balanced this one. So let's go ahead and move forward. We are given 24.1 grams of sodium sulfate, and we're trying to figure out how many grams of aluminum chloride do I need for that. So always start with the given over 1. Okay, now I want to convert from my mass of given to moles of given using the molar mass. Now I want to convert from my moles of Na2SO4 to the moles of aluminum chloride using the coefficients in the balanced chemical equation. Now I want to convert from my moles of aluminum chloride to mass of aluminum chloride using the molar mass. Now I can do my math. And when I do the math to solve this problem, I get 15.1 mole of aluminum chloride, which means that I need 15.1, sorry, I keep saying moles here, grams. And it would help actually if I canceled out my units. 15.1 grams of aluminum chloride. So if I weighed out 24.1 grams of sodium sulfate, I need to weigh out 15.1 grams of aluminum chloride for this reaction. All right, the last reaction, the last problem here, it's a little bit trickier. It's a challenge problem. This is optional. You need to predict the products for this one first. So they tell you it's a double displacement reaction. Remember, double displacement, the anions and cations switch partners. So what we're going to do is the cation for the first one, which is what's written first, it's our metal, is going to switch with the anion for the second one in the second ionic compound. And so we're going to form iron phosphate. Now I'm going to leave a little space between them because all I'm doing right now is just identifying what kind of ionic compounds that we have. I'll later go back and figure out the correct chemical formula based on the charges. So that's my first product. My second product will come from potassium, K, and chlorine getting together. So K and Cl. Again, I'll leave a little space in between. All right, so now to check if these are the correct chemical formulas, I'm going to use the charges. So starting with the first one, iron is a transition metal. It's in the middle of the periodic table here. They have variable charges, so I can't, I don't know the charges just based where it is in the periodic table. A couple of things I can do. One, if you look at the name, iron 2, the number that's in parentheses there, that 2, tells you the charge on the iron. So this is telling me it's a +2 charge. Remember, cations have a positive charge. The other way you can tell is, in addition to the name, is that chlorine, which is in group 17, and remember, things in group 17 have a -1 charge. So charges go +1, +2, skip, +3, +4, then it goes down -3, -2, -1. So chlorine's in group 17 has a -1 charge. And I have 2 of them. So I would ask myself, well, 2 times -1 is -2. So -2 plus what will give me 0? It's +2. Remember, the overall charge must be 0. So that's how I can figure out the charge of iron. Now for phosphate. Phosphate is a polyatomic ion, so you can look that up on the table, and if you did, you would find it has a -3 charge. You could, of course, also figure it out from the potassium. So potassium is in group 1. That means it has a +1 charge. And I've got 3 of them. So again, I would ask myself, well, 3 times +1 is +3. So +3 plus what will give me an overall charge of 0, and that would be -3. All right, so then in terms of the correct formula for this, if I add +2 and -3 together, that doesn't give me 0. So this is not the correct formula. I don't just have 1 iron and 1 phosphate. All right, so what do I need in order for the overall charge to be 0? I can use the crisscross method where the charge on the anion tells you the number of cations. So if the charge here is -3, then that means I'm going to have 3 irons. And the same thing for the anion, we would use the charge for the cation. So if we have a +2 charge here, that means we have 2 phosphates. Now remember, because phosphate is a polyatomic, if you have more than one, you put it in parentheses and then put the subscript on the outside. All right, for potassium, we have a +1 charge and chlorine's a -1 charge. So is this formula correct, KCl? It is, so I can just leave that as it is. All right, so now we're going to go into balancing the equations. So I got my Fe, Cl, so iron and chlorine. And then I've got my potassium and my phosphate over here. And I'm going to write the same thing on this side of the arrow. BO4. Okay, so now what I want to do is I want to do my tally, and then I'll balance it out. So I've got 1 iron right now, and I've got 2 chlorines. I've got 3 potassiums and 1 phosphate. On this side I've got 3 irons, I've got 1 chlorine, 1 potassium, and 2 phosphates. Okay, so looking at the irons, they have they're not balanced because I have 1 on the reactant side and 3 on the product side. So to change that, I put a coefficient of 3 on the reactant side. That changes the number of iron, and it changes the number of chlorine. So it's going to be 3 times 2, which is 6 chlorines. Alright, so now let's check my chlorines out. I've got 6 on the reactant side and then 1 on the product side. So that means I need to change the coefficient on the product side to 6. That changes chlorine and the potassium. So don't forget, whenever you change the coefficient in front of a molecule, all the atoms, the number of those atoms in that molecule will change. Alright, my potassium, let's check my potassium. I have 6 on the product side, but 3 on the reactant side. So I'm going to do a coefficient of 2 in front of here. That changes that to a 6. And for my phosphate, it's going to be, I have 2 of them now. And then looking at that, that looks balanced. Okay. So that's probably the hardest part of this problem, because now we're just solving. And for this problem, we want to go from mass of potassium phosphate to the mass of iron chloride. But we needed to balance it in order to get our coefficient. So let's go ahead and solve like we've been doing. So we'll take our given 15.3 grams of potassium phosphate over 1. Then to convert from grams of potassium phosphate to moles, I use its molar mass. So we'll put 1 mole of K3PO4 over 212.27 grams of K3PO4. Remember, I got that from the periodic table. Now I can convert from moles of K3PO4 to moles of iron chloride, and this is why we did all this work before, was so that we can balance that equation, get those coefficients. So I want to cancel out moles of K3PO4, so I'll put the 2 mole K3PO4. Remember that 2 comes from the balanced chemical equation. And then now I'm trying to find moles of FeCl2, so that goes there. All right. What's next? Next is to go from that to moles of to grams of iron chloride. So I have right now the moles of iron chloride. I need to get to grams of it. So 1 mole of FeCl2 goes in the bottom, and then the 126.75 grams of FeCl2 goes on top. All right. That way those cancel out and these cancel out, looking good. Okay, so now we can go ahead and just finish up with our math. Okay, so if we do, when we do this math, you multiply this all out, you get 13.7 grams of FeCl2, which means that for this problem, if you weighed out 15.3 grams of potassium phosphate, you would need 13.7 grams of iron chloride. All right, that is it for this video. So now you have your practice problems to try. For the practice problems, you'll notice that there's an answer key done step by step, and then also in the one line. If you watch this video, you want to look at the answer key for the one line work. And then there's an exit ticket. All right, have a quality day, folks.